program segment. Given ij, mn are integers and the values of m and n are given, how many times the print statement gets executed? This is the question. So now we have the for loop for I equals to 1 to m, for j equals to 1 to n. If I not equal to j, then print I plus j. You are not supposed to worry about what it is printing. You just have to see what is the inner loop, what is the outer loop. And here the question will be asked for 3 or 4 different cases when m and n are 10, when m and n are 20, when m equals to 10, n equals to 20, m equals to 20, n equals to 10. So first what we do here is we'll write the general formula. When m is equal to n, then the loop gets, or the print statement gets executed for n minus 1 times m, which is equal to m minus 1 times n. When m is less than n, then the print statement gets executed for m into n minus 1 times. When m is greater than n, then the loop gets executed for n into m minus 1. So if you consider the first and second case, here it is m is equal to n. So the loop gets executed for n minus 1 times m. So for A it is 9 into 10, for B it is 20 into 19 times. The third one, here it is m is less than n, so it is m into n minus 1 times, so it is 10 into 19 times. The next is m is greater than n, so it is executing m minus 1 times n, which is nothing but again 10 into 19 times. Next is here, for a given circuit diagram, how we can write the propositions. So here it is just P, and here between the terminals T1 and T2 you have a parallel connection with P and Q. So it is P or Q, and here third case between T1 and T2 you have series connection. So it is P and Q. So now for the given expression we need to write the circuit diagram. So here you can observe here this first expression and second expression and third expression. So between each of these expression you have a series connection. So again expression 1 is a parallel connection with the P1, P, Q and R, and the second expression is P, T, negation of Q. They are connected in parallel connection, and the third expression is P or not of T or R. So therefore P, not of T and R are connected in the parallel connection. So likewise you can draw the circuit diagram for the remaining expressions. Next we will continue with the remaining rules of inference. The next rule of inference is the rule of disjunctive conjunctive simplification. So here it states that if P and Q are true, we can say that both P is true as well as Q is true. So that is obvious. Next is rule of disjunctive amplification. So if P is true, then ORing of P with anything will also be true. Because for OR we know that if one of the expression is true, then the result is true. Therefore, if P is true, P or Q will also be true. Next is the rule of conditional proof. So here, if P and Q are true, then P implies Q implies R is also true. We can say that R is also true. So this is called conditional proof. So how this is, because here P and Q is true, therefore P has to be true, Q has to be true. So this is 1, this is 1. So here when this is 1, this also has to be 1 according to your implication. Implies. Then this has to be 1, and we know that Q is 1, therefore R has to be 1. So therefore we can conclude R has to be true. So this we call it as rule of conditional proof. Next is rule for proof by cases. So here P is also implies R and Q also implies R. Therefore we can say that P or Q will definitely implies R. This is called proof by cases. Next is rule of constructive dilemma. So here P implies Q is true, R implies S is true, P or R is true. Therefore, Q or S will also be true. Next, we'll have some note here. The upward line with an arrow is called as a NAND operator, and A NAND B is equivalent to negation of A and B, which is negation of A or negation of B. This is by your De Morgan's law. We can write like this. And a line with a downward arrow, we call it as an OR operator. It is negation of OR operator. Therefore, A nor B is equal to negation of A or B, which is equal to, again, if you apply the De Morgan's law, you will get a negation of A and negation of B.